Dear students, now we are going to see the subject transmission lines and RF system. Under that, the topic is infinite line. On completion of this infinite line, the students will be able to define the following infinite line and define the condition for an infinite line terminated in its characteristic impedance. A 2-meter long transmission line with characteristic impedance equal to 64 plus J40 ohm operating at a frequency omega is equal to 10 power 6 radian per second has an attenuation 0.0921 Nepers per meter and beta is equal to 0 radian per meter. If the line is terminated in a load of Z0 plus J50 ohm, determine the input impedance of the line. So they can able to answer all the three questions. Infinite line. From in the figure, the infinite line for the current and voltage may be written for the sending end current Is of a line of length L. Is here the equivalent circuit of the line is represented by the series of impedance ZS and the shunt arm admittance Y into ds. So the distance S is measured from the receiving end. The receiving end impedance is ZR and the sending end voltage is ES. The sending end current equation is given by Is is equal to IR cos H square root of ZY into L plus ER by Z0 sin H square root of ZY into L. Here ER is equal to IR into ZR. Substitute this ER value in above equation. So Is is equal to IR cos H square root of ZY into L plus IR ZR by Z0 sin H square root of ZY into L. In both the term IR is common, so you keep the IR as common. Is is equal to IR into cos H square root of ZY into L plus ZR by Z0 into sin H square root of ZY into L. You keep this is equation 1. The sending end voltage equation is given by ES, that is equal to ER cos H square root of ZY into L plus IR Z0 sin H square root of ZY into L. ER is replaced by IR ZR or IR is replaced by ER by ZR. So substitute this IR value in the above equation. So here the equation sending end voltages become ER cos H square root of ZYL plus ER Z0 by ZR into sin H square root of ZYL. So ES is equal to, the ER is common in both terms. So we keep ER as common. So ER into cos H square root of ZYL plus Z0 by ZR into sin H square root of ZYL. Keep this as equation 2. We know that the propagation constant gamma is equal to square root of Zy and the characteristic impedance Z0 is equal to square root of Z divided by Y. Substitute this gamma value in equation 1 and 2. So from equation 1 becomes Is is equal to IR cos H gamma L plus ZR by Z0 into sin H gamma L. From equation 2, Es is equal to ER cos H gamma L plus Z0 by ZR into sin H gamma L. The input impedance of an infinite line ZS is the ratio of sending end voltage to current. This is derived from the voltage expression E is equal to I into Ez. So sending end impedance ZS, substitute the ES and IS in ZS. So ER into cos H gamma L plus Z0 by ZR sin H gamma L divided by IR into cos H gamma L plus ZR by Z0 into sin H gamma L. So keep ZR as an LCM and IR becomes IR into ZR. So both the IR get cancelled. So numerator is ZR into ZR cos H gamma L plus Z0 sin H gamma L by ZR. In the denominator, you keep Z0 as an LCM. So Z0 cos H gamma L plus ZR sin H gamma L by Z0. So ZR is equal to ER by IR. ZS is equal to ZR into ZR plus cos H gamma L plus Z0 sin H gamma L by ZR into reciprocal of this division term, that is Z0 divided by Z0 cos H gamma L plus ZR sin H gamma L. So ZR get cancelled. So the term becomes Z naught into Z r cos h gamma L plus Z naught sin h gamma L divided by Z naught cos h gamma L plus Z r sin h gamma L. This is equation number 5. This is the first standard form of input impedance of a transmission line. Quiz question. For an infinite transmission line, the characteristic impedance is given by 50 ohm. Find the input impedance. So the input impedance is determined from the characteristic impedance only. For an infinite line, the input impedance is equal to the characteristic impedance of the transmission line. So its answer is 50 ohm only. Thank you.